Got practice example here, working on geometries. Being able to identify the molecular and electronic geometry. If you're using the reader, page 90 is what you're working on. There's also something posted online with these on our smart site. But if you're working on the textbook, that's page 374 to 375. This is to get down these things. We already did the first few. So let's go. I think we're on this one right here. Right here. I already drew out the Lewis structure, so assuming we can draw a Lewis structure. Okay, so to be able to do this is a little reminder, you need to be able to count groups. Okay? And a group could be a single bond, a double bond, a triple bond, a lone pair, or a free radical. Okay? Or an odd electron. So any of those count as one group. So when looking at the carbon, you should see two groups around it, a triple bond and a single bond. So that's two groups. So the electronic geometry is going to be linear. And the molecular geometry, because there's no lone pairs on that central atom, is also linear. What's a bond angle? Has to be at 180 if something's linear. Okay? Let's try the next one. Next one, the center atom has how many groups? You should see three, a double bond, a single bond, and a lone pair. So that's three groups. We call the electronic geometry what? We call that trigonal planar. Trigonal planar. Like a triangle. Equilateral triangle. Molecular geometry with one lone pair, though, is called what? Bent or angular. Okay? What angle are we talking about here? Yeah, for trigonal planar, it's 120, or 360 divided by 3. Try the next one. Here, the electronic geometry first. Okay, how many groups around the center atom? Should see 5. 3 lone pairs and 2 single bonds. So the total of 5. What's the 5 called? It's called trigonal bipyramidal. So it's a triangle base with 2 pyramids coming out of it. Molecular geometry now, if 3 of them are lone pairs, what do we call that? Yeah, it's linear. So when there's 3 lone pairs, then it's called linear. For linear, what's the bond angle? 180, 360 divided by 2. Okay, let's try the next one. Now there are how many center atoms in the next picture? You should see 2, the chlorine, and just to its left, an oxygen. Okay? So there's 2 center atoms. The electronic geometry, and we'll do this for chlorine first, I guess, Cl. For Cl, how many groups for Cl? You should see 4, 2 double bonds, a single bond, and a lone pair. So we call that tetrahedral. The molecular geometry, when 1 is a lone pair, what's that called? Called trigonal pyramidal. Trigonal pyramidal. So you need to get used to these names. You might not be used to them now, but over time you need to get used to these. For tetrahedral, what's the bond angle? Yeah, and remember these are ideal bond angles. A trigonal pyramidal would have slightly less, but we're only having you learn the ideal. Okay, that was for the chlorine. Let's do the oxygen just to the left of the chlorine, this one right here. So, for the oxygen, the electronic geometry, how many groups, first of all? You count 4, 2 single bonds, 2 lone pairs, that's a total of 4 groups. Again, it's tetrahedral, just like the previous one. But the molecular geometry will be different because there's 2 lone pairs. What's that called? Yeah, bent or angular, and then the bond angle is 109.5 degrees. Again, it's the ideal bond angle, but that's the angle for tetrahedral. Let's try the next one. Kind of got chopped off a little bit because of my hole punch. But that's an N. It won't matter to do the problem though. Okay, so for the next one, for this one, the center carbon has how many groups? 2 groups for the center carbon, so we call that linear. And the molecular geometry, because there's no lone pairs, is also linear. So they're both linear. When there's no lone pairs on the center atom, the molecular and electronic geometry are identical as far as names go. And the bond angle would be 180. Okay, and the last one, here at the very bottom, carbon, 3 groups around it, so the electronic geometry is trigonal pyramidal. Trigonal pyramidal, and the molecular geometry, planar, sorry. Planar. And the molecular geometry, because there's no lone pairs, is also trigonal planar. So that would be 120 degrees. Something y'all, if you haven't picked up on, you'll notice it doesn't matter which resonance structure I draw for any of these, you all should be getting the same answer. So resonance structures won't affect the shape for our class. Okay, any questions before I move on? Okay. Here, zoom out a little bit, this down here. Okay, we are on Thanksgiving Eve as far as lecture goes. Yes. You'll have a vacation from me on Thursday, and after this, we only have 2 more classes. Yeah, exciting or not exciting? Depending on your perspective. Office hours is normal Tuesday. Obviously nothing on Thursday, but today is in 3061. Okay, got this down. That was our only practice problem for today. Now we're going to resume our discussion on polarity, which is page 92 and 93, the reader. We already started it last time. Remember polarity, that's saying something is polar is saying something has a dipole. It's the same as saying something has a dipole moment. It's not 0. So non-zero dipole moment, or dipole moment, or polar, all the same thing. In the reader, I discussed 4 different ways. I started us off last time with the vector method, which is the way the textbook shows you. Textbooks running around, let's see, starting on page 379 and following for this topic. Most people don't generally groove with the textbook model, and so because of that, let me show you some different possibilities here. So you can read over what I have in the reader if you want to see different ones. I'm going to show you the 4th method, though, symmetry right now, because that's what most people will use. It tends to be the fastest and the easiest. It's also the most visual. So let's say we had one of the ones we were just looking at, OCN minus, and I had a Lewis structure drawn to look like this. We just did this in the practice example. Okay. So instead of using the Gouin dipoles and the net dipole, an easy way to do it is with symmetry. And how symmetry works, I'll write it here on the side. If you look at something that looks symmetric, then that will be non-polar. Or, in other words, not have a dipole or have a 0 dipole moment. If it is asymmetric, okay, so not symmetric, that will be polar. Why is that? Because polarity has to do with the unequal distribution of electrons. So when there's an unequal distribution of electrons, there's a pole that's set up electronically. So something that's asymmetric will be polar. So what you can do is just look at it. Is this symmetric or not? It's not symmetric, especially along this plane right here. The right side is different than the left side. And so this would be asymmetric, or we just call it polar. Okay? Purely by just looking at it. Let's try another one. Let's see the one that we just did. We did this one. Just saw this one a moment ago. Trying to determine if it's polar or not. Again, you could draw the dipole, you could draw the bond dipoles, but if you just look at it, hopefully you can see it looks symmetric. The right side is the same as the left side. So this is fully symmetric, so we would call this nonpolar. Nonpolar. Because it's symmetric, it doesn't have a dipole, no dipole moment. Yeah? Oh, okay. So he's asking, hey, there's two electrons here, that looks asymmetrically distributed. Luckily I brought my models here. The way I draw it in 2D space makes two of them look like they're on the same side, so it's kind of like this. But if you look at it, they're symmetrically distributed around the same atom in a trigonal plane fashion. So yeah, it's just my lack of ability to draw 3D-like structures. Okay, so that's nonpolar. Let's try another one. So given, again, any structure, you should be able to tell me if it's polar or not. Oh, I've got a good one. Okay, let's try CH2Cl2. Again, if you do not have the Lewis structure, you should draw that out. So you would say, oh, there's 4 electrons for carbon, there's 2 hydrogens in column 1, and then there's 2 chlorines in column 7. So you would go, okay, let's draw our skeleton. There's 4 things around that center carbon, like this. So you draw the bonds 2, 4, 6, 8, like that. Now let's do some lone pairs. So again, that's, oh, I didn't add it up. What did we get here? Is it 20? Okay, 2, 4, 6, 8 of 20. 10, 12, 14, 16, 18, 20. That'll do it. Does everything have an octet? Yeah, essentially the hydrogen doesn't, but we expect hydrogen to only have 2. So everything else has an octet. We're pretty happy. Can we do the polarity now? You might be tempted at this point to do the polarity, but especially, even if it doesn't matter what method you're looking at, symmetry or whatever, you have to draw the correct shape. And so if you have not drawn the correct shape, you can't determine polarity. The previous 3 that we've done, or 2 I guess, I already had the shape drawn, they were linear. So I didn't have to redraw them in any way after I did the Lewis structure. But this is not linear. What shape would this one be? This is tetrahedral. So I need to draw this tetrahedral. There's my template for tetrahedral. 4 atoms on. There we go. Now that I have it tetrahedrally drawn, now we can look at the symmetry. Is this symmetric or not? It's not symmetric. For example, you can see that chlorines are on one side, hydrogens are on the other. This is asymmetric, so what would we call it? Polar. Or you would say it has a dipole, or it has a non-zero dipole moment, stuff like that. Okay? So given any compound, you should be able to tell me if it's polar or not. And just as a small reminder from last time, any time a compound is polar, it will affect its chemical abilities. Alright, there's a bunch of YouTube on polarity. Lewis shape polarity 1 through 5, and there's one that has a dipole moment, called dipole moment. For some reason it's my most hit video on YouTube, but I don't know why, it's a pretty random video. So there's that. Now, if for some reason you cannot visualize this, or you're having a hard time visualizing polarity, there's one other, there's really a total of 4 I give in the reader, but not my favorite to recommend, but it does exist if you need to survive. It's method 3 on page 92, just pure memorization. And how does that work? If you look on page 90 in the reader of my VSEPR table, the last column, polar or non-polar, basically tells you for each shape what will happen. So for example, we just did a tetrahedral with no lone pairs on the center atoms, this one. It's non-polar only if all 4 groups are the same, but they weren't. 2 are chlorines and 2 were hydrogens, so it's polar. Okay, so that's how we would do the last one. We did a linear xenon F2. That was a trigonal pyramidal linear. Non-polar only if both groups are the same, which they were, so that one was non-polar. So you can use this whole table. You'll see for some of them, the bents, for example, are always polar. The trigonal pyramidal, always polar. The T-shaped and the square pyramidal, always polar. The other ones can be even. So if you want to kind of memorize through this last column here, that's another alternate way to do it. I wouldn't recommend it. It's kind of bypasses the concept a little bit, but if you need to, that can be a way to do it. In OChem, definitely, they're going to start pushing more and more towards the visual. All right, any questions on polarity? Yes. Oh, hi, yes. Okay, so on the previous one here, this example in particular, how did I know where to put the chlorines? It won't matter. If I kind of get one of my tetrahedral models here ready, I'll show you what I mean. It doesn't matter because there's free rotation in space. And so, you might not be able to, but you can rotate it out in your mind. So I drew this. If the chlorines are the blue ones, I drew something like this on the paper, but again, something like this is the same thing, it's just rotated in space. You can put the blue ones anywhere you want, or the chlorines anywhere you want. It's just a free rotation in space. It will not change your answer, and in fact, it will be identical molecules. So if you put the chlorines here, or here, or here, wherever, identical. Do you want to see chlorines here and here? That's the same thing. It would just be, let's see, one there and there. That would be this. It's just rotated. So anywhere you put the chlorines, she's wondering if they go here and here, it doesn't matter. Again, anywhere you put them, doesn't matter. It's just a free rotation in space. Yeah. Cool, good, good. Yes, oh, one more question. To make it symmetric? Okay, she's wondering about the symmetry, how does that work? And if you cut the molecule like this, it looks symmetric, but not if you cut it like this. So all planes of symmetry don't necessarily work. So it's not symmetric with regards to this slice in the plane. So that's why we would consider it not symmetric. Say it again? Yeah, she's asking, should it satisfy all possibilities? Yeah, and I put my kind of technical language in the reader. Basically, if you slice a plane, using a plane through as many bonds as possible, not including all the bonds, and you go through all possibilities there, if they all work, then it's symmetrical. Yeah, and you'll see that, that's in the 93 section 4. Again, if that doesn't end up working for you, try a different method like the dipoles or the memorization or something like that. Okay, next class we'll even do more, but I know you're going to forget a lot during Thanksgiving, so I might as well, I'll save those for a little later. There's one last section in this chapter, and if you remember this is from the reader. It's kind of summarized the past two chapters. This is the reader on page 95. Remember that using Lewis, you can determine shape, bond angles, and polarity. In order to do polarity, you have to draw the shape first. Okay? So draw the shape first, and you can do polarity. What we're going to tackle next is bond order, and kind of what will go along with that is bond length and bond energy. So we're going to tackle this next in the upper left-hand corner. I assume most of you will zone out during Thanksgiving, which is fine, but if you want to study anything, I'd recommend make sure you get the Lewis structure down, and you can do this shape, polarity, that sort of stuff. Make sure you're good at that. Okay. So let's move this out of the way. This is going to be, let's see, what page? We're going to be on page 93 and 94, the reader, and then page 382 and following in the textbook. This is kind of section 8 and 9 of this chapter. This is bond order, BO, bond length, BL, and bond energy, BE. Okay. Bond order. How does that work? You have two atoms bonded with a single bond, we call the bond order 1. Two atoms with a double bond, bond order 2. Two atoms with a triple bond, bond order 3. Can you have a bond order that's not a whole number? It's possible, actually. Yeah, especially in the next chapter, but even in this chapter, you've seen it. Let me show you an example. You've seen this molecule. So the bond order of the bond on the left right now is 2. On the right is 1. Okay? That would be the bond orders. But you also learn this as a resonance structure. The resonance structure would be this. There's a resonance structure. Now the bond on the right is 2, the bond on the left is 1. And so the bond in total on the right, this one, is half of the time 1, and the other half of the time 2. So on average, this bond is 1.5 bond order. Half the time it's 1, half the time it's 2. Same for the left-hand side, half the time it's 2, the other half the time it's 1. So on average, it's 1.5 also. So this can be an example, and anytime there's resonance, you can have a bond order that's not a whole number. In the case of this, here as another one, this is the nitrate ion. There we go. There's a nitrate ion. The bond order on the top right now is 2 for a double bond, but it'll have resonance. So there's a couple resonance structures here. One that looks like this, just to draw it really simply, and not without the lone pairs. Well, another one that looks like this. What would be, if those are the 3 resonance structures, what's the bond order for the bond on top? Yeah, over 3 resonance structures, there's a total of 4. A 2, a 1, and a 1. So in the first case it's 2, second case it's 1 for the bond on the top, in the third case it's 1 for the bond on the top. So 2 plus 1 plus 1, total of 4. Divided by 3, or 4/3, or 1 1/3 in this case. Okay? So you can definitely have bond orders that are not whole numbers whenever there's resonance structures, and there'll be other situations in the next chapter as well. That's bond order. Okay? Let's go back now. Bond length. That's just simply the distance between 2 nuclei. So this will be the bond length. I mentioned it before. Simply that. I'll say a little bit more about it in a moment, but it tends to be the sum of the covalent radii if it's a covalent bond. Okay, and then the bond energy is simply the energy stored in the bond. We kind of think of it as almost a potential energy or a chemical potential, and that would be the bond energy BE. It's the energy stored within a bond. There are some calculations in your textbook that we're not going to do. You really do those in Chem 2B. But what we will talk about is the follows. What's the relationship between those two? Go to the next page. Okay. So I'm going to draw a little continuum. Here's the bond order. Bond order typically goes from 1 to 2 to 3. So let's say it increases to the right. What happens is the single bond will be on the left, then the double, then the triple. The triple bond has how many electrons in that bond? 6, so it has more electrons than the single, which has 2. But because it's so strong, it draws the nuclei closer to each other. So actually the triple bond is the shortest bond. Because it's so strong, it pulls the nuclei towards each other. So in fact, bond length is the opposite of order. Meaning as the order goes up, the bond length goes down. Or vice versa. The bond length goes up, the bond order goes down. So they're opposites of each other. The bond order and bond energy, however, follow each other. Bond order and bond energy follow each other because as you put more bonds in there, it has more potential. It's storing more energy in each bond. Now, a double bond isn't twice as strong as a single bond. It's a little bit less, and you'll see why in the next chapter. And the triple bond is not 3 times as strong. But they have increasing energy as you go through the bond order. So, for example, if we look at the last picture in your notes here, let's do this. Okay, I have the sulfur dioxide and the nitrate ion. Which one has longer bonds, the top or the bottom? Which one has longer bonds, top or bottom? The one, so as bond order goes down, so this is 1.3, just do the calculation for you. This is 1.5. Okay. Well, I'm hearing something in my head. Feels like my alarm clock. Okay, I almost can't concentrate. I'll try here. The bond order for the bottom one is shorter, so the length is longer. Okay, so this one is a shorter bond order, so a longer bond length. So the nitrogen-oxygen bond length would be longer here, and this one with a higher bond order will have a shorter bond length between the sulfur and oxygen. Okay? So the bottom one, having the smaller bond order, will have the larger bond length, and this will have the smaller bond length up at the top. Okay? You can do the same with bond energy. As the bond order goes up, the bond energy will go up. So the higher bond order here will have the higher energy in the top one. Okay, so make sure you know how these three correlate.
Question.
Yeah,
Are we ever going to have to quantify the bond length?
Are we going to have to quantify bond length? Not necessarily, but you could be given, and we're not going to do this question right now, but just an example question, you'll see them on the practice finals, where we give you two other lengths, and based on what kinds of bonds those are, you could kind of estimate the bond length of another. So that's possible, but that's as far as we would go. Okay? So, given what the length of a single, a double, and another single, they'd ask you about another bond. Okay? That's as far as we go. All right. That's the end of the chapter. Let's see, did I have any, I don't know if I showed this bond order from Lewis is what we just did. All right, we finished the chapter. If you're curious, there's actually another way to do Lewis structures that I put in my reader on page 96. So if you want to take a look at page 96 and 97, it takes a while to get used to. But if you want to look at it, you can. I won't do this method in class, but it is a faster way to draw Lewis structures than what we've done before. In general, it is. And the other advantages to it in OChem, that method that you see there is typically what you'll use in OChem. So it's up to you if you want to learn that method or look it over. But otherwise, we've finished chapter 9. We're going to our last chapter, and we've done everything. If I cover this side here, we've done everything on the left-hand side. Shape, polarity, bond angles, bond order. Okay? So that was all chapter 9. Chapter 10 is going to get into this on the right-hand side.